Good morning, students. So, in this class, we are going to see what is an overvoltage and what are its effects, and how the overvoltage is caused in a transmission line in the subject of high voltage engineering. So, what are the causes and its effects in the transmission line? It will be explained in detail in this class. So, just visualize this video. Thank you.
We have seen about the overview of the lightning waveform. What is the necessity to give the protection against overvoltage? So in today's session, we will be seeing about what are the causes of overvoltage. It can be either due to your internal causes or it can be due to the external causes. So when I say it as external causes, mainly lightning peeps in. So whenever I am going to say lightning, it is nothing but we have seen it is a steep fronted waveform wherein the voltage rises to several times the normal value. If this lightning is going to usually it will strike the transmission line, in that case it leads to the insulation breakdown. Of course, if this overvoltage is going to be let for a period of time, then in that case it will cause considerable damage to the equipment. So it becomes utmost necessity that protection against these type of lightning should be provided by using the lightning arresters and other devices. Now we will move on to your internal causes. Under internal causes, you have 4 sub-classifications. It could be due to either due to your switching surge, or it can be due to your insulation failure, or it could be due to the arcing ground, or it could be due to the resonance. So first we will analyze the switching surge. Now what is the switching surge? So the surge which is going to be caused due to the switching operation, that is called as your switching surge. When the switching operations will take place, whenever I am going to open the circuit breaker or I am going to ground the line, during the switching operations there is a possibility of the switching surges occurring on the line. Now under this switching surge, we are going to analyze whenever the line is going to be unloaded or it is going to be a open line. And in the next case, it can be due to a loaded line. So in this case, what are the problems that occurs in the transmission line? Now let us take the first case wherein I am just putting a voltage source and I have connected to the no load line. That is, the line is not loaded at all. So whenever I am going to close the switch, what happens? This voltage will move and it reaches the point A. Since there is no load connected, what will happen? So this voltage will reverse back, which causes a traveling waves in the transmission line, or a surge is created here. So here in this case, if you could see, the voltage will rise to twice your maximum value. Okay, you know your VRMS is equal to Vm by root 2. In that case, if I want to express in terms of the instantaneous value, the instantaneous voltage value that will be on the line, it is nothing but 2 into root 2 into your E. So this high voltage can damage the equipment. Of course, when this voltage, this is going to be a transient and it will take certain time to come back to the normal, and the losses also will be there. So in that case, again it will restore to the normal value E. But at any instance, if the line is going to be unloaded, in that case, a rise of 2 into root 2 into E times the voltage gets increased. Now we will analyze the loaded line. What happens if the loaded line is going to be considered, right? Now, what is the formula V? You know, it is nothing but I into R. Already we have seen it will rise to the value of 2 into root 2 times E. Now I am going to write in terms of the current and impedance. Here I have just considered a small problem where the current is going to be 100 amps and the impedance is going to be 1000 amps. Since it is going to be represented in kV, if you could see after doing the calculations, it comes out to be 282.8 kV. Just for a simple example of 100 amps and 1000 ohms. Okay, in this case, if you are going to see what will be the maximum voltage, then the initial voltage, that is your initial maximum voltage Vm plus whatever is this increase, 282.8 kV. So this is quite a cumbersome value which cannot be neglected. So such high voltage will be induced in the line. So suitable protection mechanism is required. Now we will move on to the third case. What is this third case? It is nothing but the current chopping. So when I say it is the current chopping, this is the phenomenon which is usually seen in your circuit breakers. So I already told you in circuit breakers, whenever the circuit is going to be opened, there is a problem of arc interruption. If this arc is not going to be suitably interrupted soon by your circuit breaker dielectrics, it will re-arc and it will create a short circuit and it will damage the system further. Okay, here whenever I'm going to say it as a current chopping, it is nothing but in case of AC circuit breakers, we try to quench the arc at natural zero. Whenever it is going to reach the natural zero, we'll try to quench the arc. But if you are not able to quench the arc and you're going to quench the arc before the natural zero. Whenever I try to quench the arc before the natural zero, this process is called as current chopping. Okay, what will happen? So if I'm going to quench before the natural zero, there is a problem of restriking again. So you will again have a high steep of voltages which is penetrating. So you will have, suppose if I'm going to quench here, I will have a very high voltage. So in this case, you can prevent it by using a resistor switching so that all the currents are getting drained to ground. So what is current chopping? It is nothing but, so you are going to chop the current before the natural zero is reached. Now we will move on to the next condition, that is your insulation failure. Here it has been considered only a single line to ground fault. Okay, in this case I am just considering here the impedance on one side it will be E by Zn. On the other side, it is minus E by Zn. But in this case, both the currents, that is E by Zn is nothing but the current magnitude. Here, in this case, whenever a fault occurs at this point of the line, both the currents are going to be drained to the low resistance path. In this case, here I have E minus E by Zn minus of minus E by Zn. So, twice the amount of your current is going to flow through in case of a insulation failure. Now, we will move on to the arcing ground. Arcing ground is nothing but usually what is the intermittent arc that is going to occur due to a LG fault in a line to ground fault in a three-phase line. What happens usually in the olden days, this three-phase line will not be neutral. That is, it will not be connected to the neutral point. Why? Because what happens if at all a fault occurs? So in that case, what will happen? So the arc, that is, it is not required that you have to remove the line because you have not connected it to the neutral. Okay, and the second thing is that whenever I'm not going to connect it to the neutral, what will happen? The zero sequence current, whatever, if it is going to be connected, then it will be circulating. So that process is also avoided. So these two advantages were there. Okay, I don't want to remove the line out of action if I'm not going to connect to the neutral, and the zero sequence currents are eliminated. But this will not suit to all the conditions. Whenever there is going to be a high fault occurring on the system, then this might lead to a considerable damage of the equipment, right? So in this case, so whatever is this intermittent arc, which is going to be usually it is going to persist during your line to ground fault in a three-phase system with the occurrence of your transient is called as your arcing ground. How can this arcing ground can be prevented? It can be prevented by using if I'm going to earth the neutral, in that case arcing ground can be prevented. The last case, that is the resonance. All of us know what is resonance. Whenever my circuitry, that is my inductive reactance is going to be equal to my inductive capacitance, then it is going to be at the resonance condition. In this case, what happens? My impedance is going to be equal to your resistance and the power factor is going to be unity. So whenever this value is going to be reaching, what happens? It is going to result a very high over voltage in the system. Whenever you are going to see what happens, usually in case of your transmission line, the inductance value is going to be more when compared with your capacitance value. So in that case, whatever is the resonance which is going to occur on a transmission line is quite rare. Okay, so with this I conclude today's session. In the next session we will be seeing about the mechanism, what is lightning discharge and what are the mechanisms of lightning discharge. Thank you.
So, in this class, we saw about various external and internal causes of over voltages. So, in the next class, the next video, we will be seeing about lightning mechanism, right? Thank you very much. Thank you.